Bonds form to fulfill the octet rule. So we talked about this when we did the ionic bonds. Okay, and atoms tend to gain, lose, or share electrons to have 8 electrons. Okay. So far with ionics, we talked about gaining or losing. Now we're going to talk about sharing. The 2 exceptions to this rule are hydrogen and helium, who only want 2 valence electrons. So there are 3 types of bonds: metallic bonds, ionic bonds, and covalent bonds. Metallic bonds are easy. They're formed between metals. So metallic bonds are formed between metals, and we'll cover them later on. It's just metal to metal, and they're very, very easy because there's not much to it. Ionic compounds are formed by ionic bonds, and these form between metals and nonmetals. They have a difference of electronegativity greater than 1.7. Because of this, the highly electronegative nonmetal has such a stronger attractive force to the electrons of the metal, it steals electrons until both atoms have full outer shells. So this is how ionic compounds satisfy the octet rule, is by stealing and giving electrons, and therefore someone ends up with 8 and someone has lost their outer shell, so their lower shell has 8. So this loss and gain of electrons creates cations and anions that are held together by the positive and negative attraction. So like I said, this won't go away, but we need to keep this as an entirely separate thing from what we're going to start talking about today. So ionic was a metal and a nonmetal. Covalent is going to be between nonmetals. So we're only talking about the upper right-hand corner of the periodic table. For all nonmetals, they have high electronegativities. So the difference in electronegativity is less than 1.7. So electronegativity is the ability to attract an electron. All of the nonmetals are really capable of attracting electrons. Nobody's weak enough to just steal an electron from, so you can't steal electrons anymore. Because of that, because our nonmetals cannot steal electrons from other nonmetals, they are attracted to both nonmetals and therefore shared between the atoms. So these 2 atoms, they're both pulling. So if I have 2 oxygens, they're both very electronegative, so they're both going to pull on each other's electron in order to satisfy these 2 atoms. So we end up sharing these 2 electrons. Our outer orbital of both will just overlap. So that way the electrons can go between both of their orbitals. And between that, now they both are satisfied. You can count on this side, you can count on that side, and everyone's going to be satisfied. So a nonpolar covalent bond, so nonpolar. When we think of poles, think about the North and the South Pole. You have 2 extremes. One's really, really high and one's really, really low on the globe. Having 2 different areas, the top and a bottom, or a positive and a negative end, is what we're going to be talking about with nonpolar and polar. Nonpolar means there's no extreme. You can't say where a top and a bottom is. You can't say where the positive or the negative is on a molecule. So we have a nonpolar bond if the nonmetals have the same electronegativity, so the electrons are equally shared. All 7 of the diatomic elements are nonpolar. Neither one of these oxygens are more capable than the other one of attracting these electrons, more so than the other one. Because of that, they equally share these electrons, and there isn't a positive and a negative end. Based on the picture of the oxygen molecule, draw the chlorine molecule here. You're going to come back to do that for homework. So what's the difference between that and a polar covalent bond? Well, a polar covalent bond is if the nonmetals have a difference in electronegativity. Okay, if one of them is stronger at pulling on those electrons than the other one, then the electrons will still be shared, but they're going to be shared unequally. In other words, they are unevenly matched, but willing to share. I want you to think of tug of war when we're talking about a polar bond. An ionic bond, the tug of war ends the second the 2 atoms get near each other. One of them just rips the electron off the other, voila. In a covalent bond, they're playing tug of war. They're both attracting those electrons. If it's nonpolar, they're a perfectly even match. Those electrons are stuck right in the middle. So there's no positive and negative end where there's more electrons on one side than the other. But a polar covalent bond is where they're both strong enough to keep playing, but one of them's weaker. So you know the flag in the middle whenever you're playing tug of war? That flag is where your electrons are, and those electrons are closer to the stronger atom. Because those electrons are closer to the stronger atom, electrons means negative, right? That one atom will be slightly more negative than the other one. So we have a negative end and a positive end. That's what polar means. You have two poles, a negative end and a positive end. It's not like ionic, where you have something that's really negative and really positive. It's taken an entire electron or more. But it's slightly holding on to that electron a little bit more, so therefore it's slightly negative. This is very crucial when we're going to be talking about water. Okay? So let's go through these notes to go on further with that concept. So this uneven sharing of electrons creates a slightly positive and negative charged end. This is why they are called polar. They have a positive and a negative pole, like the North and South Pole. So example, water is a polar covalent bond. Oxygen's electronegativity is 3.4, hydrogen's is 2.2. So when you subtract that, it's only 1.2. It's less than 1.7. So hydrogen's still able to put up a fight for these electrons, but it's not nearly as strong as oxygen. Because oxygen is more able to attract the electrons to itself, therefore it has a slightly negative charge. While hydrogen is only slightly attractive to the electrons and therefore has a slightly positive charge. So that's what we have here, a slightly negative and a slightly positive end. This right here is what creates all of the crucial things about water that makes Earth habitable for us. Okay, things like the fact that ice expands whenever you freeze water. It expands because the hydrogen bonds between different water molecules connect. The fact that things dissolve in water, why you can pretty much dissolve most things in water, is because water is polar. So it's able to pull apart other things. Salt dissolves in water because it's polar and it pulls apart the salt ions. Okay, so this polarity is going to be very important. But for now, I want you to really get down the concept of being covalent, first of all, is sharing electrons. If you are nonpolar, you share those electrons evenly. If you're polar, while you still are able to share, while you're still both putting up a fight for those electrons, one of them is stronger, and whoever's stronger is slightly negative because he's holding on to those electrons a little more. So far we've focused very strongly on naming and formula writing for ionic compounds. Now we need to learn it for covalent compounds, but before you freak out, it's really easy. This is the one page for covalent, okay? So now the most important thing, though, is that you can keep them separate. You need to first identify, is it ionic or is it covalent? So first you identify, is it a metal and a nonmetal, or is it just nonmetals? If it's a metal and a nonmetal, keep doing ionic. Do not confuse ionic with what we're going to learn today. If it's only nonmetals, then we use covalent. So covalent compounds are named using Greek prefixes to indicate the subscript number. With ionic compounds, the charges decided the subscript number, so you didn't need to write down what each subscript was going to be. Okay, you wrote down what the charge was for transition metals and the other metals, because that doesn't automatically given to you from the periodic table. But in covalent compounds, they're not formed based off charges. They're formed off of sharing electrons, and so they can have different numbers. You can have carbon monoxide, which is CO. You can have carbon dioxide, which is CO2. You breathe out CO2. If you breathe in carbon monoxide, you die. Okay? There's a big difference here. So part one, how do we write the formula for a covalent compound? Well, you write the symbol of the first element, followed by the subscript indicated. Repeat for the second element. So all you really need to know are these prefixes. So if I have my example here, dinitrogen trioxide. Well, nitrogen is N, so we do N. Di means 2. You already know that. So it's N2. And then trioxide, well, oxygen is O. And tri means 3, so we have O3. So when you look at these prefixes, you need to know them. So number 1 is mono. The only thing is this will never be used on the first element. So carbon dioxide. We don't say monocarbon dioxide. If you don't say a prefix, then you just assume there's only one on the first one. So it's just carbon dioxides, because 1 C, 2 O's, di. 3 is tri. 4 is tetra. Now people sometimes struggle with this one. I'm going to make it real easy for you. Da na 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 na. Na 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 na. Tetris. T-E-T-R always means 4. Every piece of Tetris has 4 squares in it. Every single piece of Tetris. That's what the name means. It is a puzzle of 4-piece puzzles. Okay, so tetra, Tetris. We good? That's the only one people usually struggle with. After that, penta means 5. We know that. Hexa 6, hepta 7, octa, nona, deca. We should know all those. Make sure you get tetra. So, how to name covalent compounds. So we just looked at how to write the formula, how to name it. Well, you write the Greek prefix for the first element, subscript, unless it's the 1, followed by the full name of the element. Then you write the Greek prefix for the second element's subscript, this time even if it is 1, followed by the root name and "-ide". So no matter what, you end them in "-ide". Okay, just like the last nonmetal in an ionic compound ends in "-ide, the last nonmetal of a covalent compound ends in "-ide". So this time if I'm given N2O5, we know we have 2 N, so I need to write that in the name because I'm not given a charge. Charges don't decide these subscripts, so I have to actually tell you what is the subscript. If I just say nitrogen oxide, you have no idea what the formula is because there's no charges to tell you what these subscripts are. So you gotta say what are the subscripts. So N2, 2 means di, N is nitrogen, so I have dinitrogen. 5 is penta, so I have penta-ox, and once again we change it to "-ide". So dinitrogen pentoxide. Okay. We don't double up on the vowels here, so we don't say pentaoxide. Okay. If we're ending in a vowel, we just switch out that vowel for the one that's already there. So let's look at a couple of these. How about dinitrogen trioxide, right here, N2O3, 2 nitrogens, 3 oxygens. That's it. Bromine pentafluoride, Br, doesn't say mono because we don't need the mono. If we don't do a prefix, it just means 1. Pentafluoride, F5. So then to write the names, if I have KRF2, I don't put mono on the first one. So I just say krypton, di, fluoride. Change the end to "-ide". And for number 3, sulfur, tetra, chloride. Don't put mono on the first one.